Welcome to GERO Mathematics and Statistics lessons. Today I'm going to be talking about the binomial theorem. The binomial theorem and Pascal's triangle. The binomial theorem and Pascal's triangle. Okay, so I'm going to be discussing this in this video. Now, let me start with telling you about the binomial theorem and Pascal's triangle. These two ideas enable one thing. They help you in expanding what is called a binomial. So, let's start with seeing what a binomial is. Now, the idea of a binomial comes from what is called polynomials. And please, I want you to go back and watch my video on polynomials, okay? It will make you understand in detail what a binomial is. So, let's start with a binomial. For us to start with a binomial, I'm going to choose, say, two letters or variables, x and y, representing real numbers, okay? So let x and y be real numbers. And in particular, let n be a natural number. A natural number, in this case, including 0. Okay? Then, what is called a binomial? What is called a binomial is a two-termed polynomial. That is x plus y. Is a two-term polynomial in two variables, of course. Okay, so if we use x and y that are real numbers expressed in this form, then we will be talking about a two-termed polynomial. Okay, that is the reason why I'm emphasizing you go back and watch our video on polynomial. But let me just tell you or remind you that a polynomial describes the sum of separate terms of positive non-zero non-fractional powers. It is the sum of separate terms of positive non-zero non-fractional powers. So notice it can be in one variable, it can be in two variables, but a binomial is particularly in one or two variables, but expanded or expressed in this form. Take note. What brings about the idea of a binomial expansion and the idea of Pascal's triangle is to deal with problems where a binomial as this could start having powers of expansion. For instance, the task may be to obtain this. The task generally, is to obtain an expansion for this, where x and y are members of the real number system and n is a positive integer which can be 0. Okay? If you look up on our videos on numbers, you will remember or you would see that we had discussed this type of natural number system. There are two types of natural number system. There is the belief by some group of mathematicians that the natural number system begins or should include 0. So for that type of natural number system, you have this. And there is another natural number system that excludes 0. So that natural number system begins with 1. Okay? So note that I have not used this in my description. Rather, I have used this. So when we say x and y are members of the real number system, meaning that they are real numbers, we are saying that n must be from this type of natural number system where, of course, 0 is among. Okay? So the essence of discussing the theories or the theorem of binomial and the Pascal's triangle is to tackle the expansion of what is called a binomial, in this case a two-termed polynomial expressed in this manner, x plus y. Remember, polynomials can be in 2 variables, 3 variables, or 1 variable, okay? So, but what is important is that it must be the sum of separate terms of positive, non-fractional, non-decimal powers. Now let us see, how do we expand this? To understand the expansion of this, let us start with Pascal's triangle. So Pascal's triangle was a development. Pascal's triangle was a development initiating the genesis into the expansion of problems of this nature. So what that triangle is all about is this. A triangle describes the coefficient in the expansion of problems like this. So let us start with taking a simple problem, x plus y raised to power 0. X plus y raised to power 0, according to Pascal's triangle, would have only one term having a coefficient 1. If you move over to x plus y raised to power 1, according to Pascal's triangle, this expansion, the expansion of this, would have 2 terms having coefficients 1 and 1. If you move over to the expansion of x plus y raised to power 2, according to Pascal's triangle, you would have 1, 2, and 1. And if you move over to the expansion of x plus y raised to power 3, according to Pascal's triangle, you are going to have 1, 3, 3, and 1. If you move over to the expansion of x plus y raised to power 4, according to Pascal's triangle, you are going to have 1, 4, 6, 4, and 1. Now, having done that, I want you to take or pay particular attention to the following. Take note that when the power is 0, we have 0 plus 1 term. That is, there is 1 term when the power is 0. When the power is 1, notice that there are 2 terms. So the number of terms is 1 plus the power. Take note of that. Now, when the power is 2, notice there are 3 coefficients, meaning that there are 3 terms in the expansion. When the power is 3, take note there are 4 terms in the expansion. When the power is 4, take note there are 5 terms in the expansion, and this continues. Now, if you have ever expanded before, you would come to realize, if you've done certain expansions before, you would come to realize that you will come to realize the following. So, for x raised to power 0, according to what we had discussed in indices, x raised to power 0 will give you 1. Okay? Now, x plus y all raised to power 1. Remember, from indices, anything raised to power 1 will give you that thing. So it brings x plus y. Now, what is the coefficient of x? It is 1. What is the coefficient of y? It is 1. And you can clearly see that gives 1, 1. Okay? Now, if you come over to x plus y raised to power 2, you would notice to expand this using our simple knowledge of expansion earlier on, you will come to realize this is what we did. And x multiplied x to give you x squared. X multiplied y to give you xy. And y multiplied x to give you xy. And then y multiplied y to give you y squared. And notice, this simplified by like terms, this will add to give you 2xy, and this gives y squared. Notice that in the final expansion, you have 1, 2, 1. As the coefficient, 1 being the coefficient of x squared, 2 being the coefficient of xy, and 1 being the coefficient of y squared. And this gives 1, 2, 1. If you had expanded this ever, x plus y raised to power 3, you would notice this would have given you x plus y times x plus y times x plus y. And this would simplify to x plus y times what the product of this gives, which is x squared plus 2xy plus y squared. And this, when you use this to multiply everything here, you would have x cubed plus 2x squared y. X times y will give you x times y squared will give you xy squared. Then you now start using this to multiply everything here, and that will give you x squared y plus 2xy squared plus y cubed. And if you simplify this by taking like terms, this would have given you x cubed and 2x squared y, and this will give you this would have given you 3x squared y rather, because this would add to this, they are like terms, and this would add to this, and this would have added to this to give you 2xy squared, and finally you have y cubed. Okay, so if you look at the final expansion, you will notice you have coefficient being 1, 3, 3, and 1. So this describes what we refer to as the Pascal's triangle. Now notice what the Pascal's triangle does for us. It helps us to expand in the sense that it tells us the coefficient in the expansion of a binomial. It tells us the coefficient of the expansion of a binomial. So summarily, for Pascal's triangle, we are going to write 1 when x plus y carries the power 0. When this binomial carries power 0, we are going to write when it carries 1, 1 and 1. We are going to write when it carries 2 as its power, 1, 2 and 1. We are going to write when it carries 3 as its power, 1, 3, 3 and 1. We are going to write when it carries 4 as its power. When it carries 4 as its power, we are going to write 1, 4, 6, 4 and 1. Now take note of one thing. It is very simple to develop the Pascal's triangle. What I usually tell my students is starting from this one, add a 0 to the right and to the left. When you add a 0 to the right and to the left, it gives you 1. 1 plus 0 will give you 1. 1 plus 0 will give you 1. Now add another 0, add this to itself and add another 0. If you add this, 1 plus 0 will give you 1. 1 plus 1 will give you 2. And 1 plus 0 will give you 1. Now repeat the same procedure. Add a 0 here, add a 0 here, and then add these terms. If you do that, 1 plus 0 will give you 1. Okay? 1 plus 2 will give you 3. 2 plus 1 will give you 3. 1 plus 0 will give you 1. If you repeat the same procedure, 1 plus 0 will give you 1. 1 plus 3 will give you 4. And 3 plus 3 will give you 6. 3 plus 1 will give you 4. And then 1 plus another 0 will give you 1. Now you can continue doing this even up to x raised to power 5 and beyond. You will notice that I don't need anyone to tell me that plus a 0, this gives 1, plus 4, this gives what, 5, plus 6, this gives 10, plus 4, this gives 10, and plus 1, this gives 5, and finally 1 plus 0 gives 1. So that is Pascal's triangle, and it is very simple to develop. Remember, Pascal's triangle helps us to expand. So this will be a part 1 video on binomial theorem and Pascal's triangle. Let us see. Now, I haven't talked about that for Pascal's triangle. Let us go quickly to the binomial theorem. So, the binomial theorem. Now, take note. The binomial theorem overcomes a particular problem of the Pascal's triangle. What if, so let me write that down. The binomial theorem overcomes deficiencies of the Pascal's triangle, meaning that the binomial theorem is superior in its efficiency to that of the Pascal's triangle. Now, why is that so? Let's see. Reasons. Number one, Pascal's triangle becomes complex and space consuming for very high powers of binomials. So it becomes very difficult to use Pascal's theorem if you want to describe binomials or expand binomials with very large powers. So, for instance, if I gave you x plus y raised to power 100, it becomes very difficult to do what we've done using Pascal's triangle. Number two, Pascal's triangle is also complex and time consuming to obtain coefficients of terms in an expansion with high power. So in an expansion with high power. So if I had a problem like this given to you, x plus y raised to power 70, and I required that you gave me the you determined the coefficient of the 50th term. If I wanted you to determine the coefficient of the 50th term in this expansion, so it will be a very big problem using Pascal's triangle. So two main reasons why Pascal's triangle is not efficient is, number one, Pascal's triangle becomes very complex if the expansion of the binomial has a power that is very high. Number two, Pascal's triangle becomes inefficient if you seek to determine the coefficient of an expansion, a binomial expansion, having a power that is very high. So if, for instance, I tell you in this expansion x plus y raised to power 70, tell me the coefficient of the 50th term, it becomes very difficult for us to do or to get. Okay? So that brings me to what then does the binomial theorem do? So I'm going to take the binomial theorem and let's see what that is. Okay? Let's see what the binomial theorem talks about. So, the binomial theorem is summarized as follows. So, let's start with saying the binomial theorem describes the expansion of a binomial of positive powers with zero inclusive, and is summarized as follows. Number one, the first thing that binomial theorem speaks is that every coefficient in a binomial expansion must be combinatorial in nature. Full stop. So it means that in the binomial theorem, the coefficients of terms in the expansion must be combinatorial. I'm going to explain what that means. Number 2, as you move in a binomial expansion from left to right, the expansion which starts with the highest power, as you move from left to right in the expansion, or in a binomial expansion, as you move in a binomial expansion from left to right, the expansion which starts from the highest power gradually decreases from the highest power to the lowest, or to zero for the first term, but it increases from 0 to the highest power for the second term. So, binomial theorem also tells you that as you start expanding, moving from left to right, take note, the power of the expansion begins for the first term. Let me show you what that means. See what that means here. For instance, x plus y all raised to power 3 would give you x raised to power 3. At this point where x is 3, take note y was 0, the second term. The first term begins with 3, which is the power of the expansion. And take note, we are moving from left to right. Now, at this point, after x raised to power 3, y raised to power 0, comes 3x raised to power 2, y raised to power 1. Note, moving from left to right, x carries a power that keeps decreasing by 1. In this case, it decreased from 3 by 1 to 2, and it brings us to the next one, where it decreases to 1, and note something about y. Y started with 0 and has increased to 1. Here it would increase to 2, while x would drop by 1 again to give 1. Finally, it gives us x raised to power 0, y raised to power 3. So as you move from left to right in a binomial expansion, the expansion which starts with the highest power, in this case 3, for the first variable, keeps decreasing by 1 as you move through each term, while for the second term it keeps increasing from 0 to the highest power 3. So Pascal's binomial expansion also talks about that. Number 3, in the binomial expansion, the sum of the powers in each term adds to give the total power, or the power of the expansion. Okay, so notice that at every point, 3 plus 0 gave me 3, 2 plus 1 gave me 3, 1 plus 2 gave me 3, 0 plus 3 gave me 3. What is 3? 3 is the expansion power. Okay, so the sum of the powers in each term adds to give the total power, or the power of the expansion. Then finally, number 4, take note of something about the binomial expansion. Take note of something about the binomial expansion. Now, using the binomial theorem, in the binomial theorem, a power of n for the expansion implies that the final expansion implies that the final expansion will have n plus 1 terms. Now, what that means is this. Look at this problem. If the expansion carries a power of 3, the final expansion will have 3 plus 1 terms. That is 4 terms. 1, 2, 3, 4. If the expansion were to be x plus y raised to power 2, this would have given you x squared plus 2xy plus y squared. Note again, if the expansion carries a power of 2, the total number of terms will be 3. That is 2 plus 1 terms. 1, 2, 3. So what this particular statement about the binomial theorem is saying is that in the binomial theorem, if the power of the expansion is n, then the final expansion would have n plus 1 terms. So the number of terms you have in an expansion is always 1 more than the power. Okay, so we are going to be looking at expanding in our next video on the binomial theorem and Pascal's triangle. I'm going to be showing you how to expand problems using or binomial expansion, how to cater for binomial expansions using the Pascal's triangle and the binomial theorem. I'm also going to be showing you how to predict terms or the coefficient of terms in a binomial expansion. I'm going to show you how to do that in the next video on binomial theorem and Pascal's triangle. So like our video, share our video, watch our video extensively to learn a lot, and most importantly, keep subscribing to our YouTube channel. Thank you, and I'll see you in a bit.